Hello friends, this is lecture number 22 of complex analysis, and today we're going to discuss about residue theorem. And this is my Insta ID was Lakhyajit 123. If you want to follow me, then you can follow me on Insta. Okay, and if you want to watch all the previous lectures, then you can get those in the playlist that's gonna appear at the end of this video. At the end of this video, at the end screen, you can see there will be a playlist. Okay, and then click the playlist and you can have all the videos. Okay, so or you can just check in my channel playlist. Okay, and before we start, please subscribe the channel, hit the thumbs up button as well, and also share with your friends. Help me to create help me to grow my channel and inspire me to create new contents for you. And to hit the bell icon, just do hit the bell icon so that you get notified when new video will be uploaded. Okay, and stay connected. So now let's start. So what is the residue theorem? Here you see, let me write the residue theorem. Okay, if we have a function f of z which is analytic at a closed in a closed curve C, suppose in a closed curve C, that is C, and except at a finite number of poles within C, right, within C, then the integration f of z dz over C is given by 2 pi I times the sum of all residues at the poles within C, So what does it mean? Suppose, so here is the region, here you can see this is the region C, this is the curve C. Okay, suppose a function is analytic here, f of z, this is analytic except at a finite number of poles. Suppose we have finite number of poles, maybe a1, a2, and so on, a3, right? These are the poles within C, right? Then the integration f of z according to this theorem over C is given by 2 pi I times the sum of the residue at the poles within C. That means, so here this is a1, this is a2, and here it is a3. So residue of this function f of z at a1, residue of the function at a2 plus dot 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 and so on. So sum of these residues into 2 pi, this gives the integration of f of z over this curve C, right? So that is the residue theorem. So now let us prove this. So how to prove this? Let me cut it. Now let me go to a new slide in order to prove this. So first let us consider closed curve. Suppose this is the closed curve C. Let me consider it. Okay, then we have considered C1, C2, we have considered C1, this is suppose C1, this is C1, so center at A1, this is C1, and similarly let us consider this is suppose C2 at its center at A2, this is C2. Okay, and this the larger circle is C, suppose, and so on. We have considered such n circles. These are non-intersecting circles. Okay, centers at A1, A2, A3, these are the non-intersecting circles. Okay, and so on. So we have considered this way. Now you see that in Cauchy's integral theorem, Cauchy's integral theorem for multiply connected region, you have got that we have already discussed. So for better understanding, just what's the previous lectures, all the previous lectures. Okay, so we have got that if this is C1 and there is another circle, suppose C2, we made cuts here for this. We have got that C1 integration over C1 f of z dz is equal to integration over C2 f of z dz. We have got this in Cauchy's integral theorem, Cauchy's theorem for multiply connected region. Okay, suppose instead of one small circles, if we have many small circles c1, c2, c3, so on, then we have to take the sum here. Then we have to take the sum plus c3 and f of z dz and so on. Okay, so if we apply that theorem, then what we can write? So first let me write what I have considered here. So first let us consider, so this is the proof of residue theorem, proof. Okay, so let c1, c2, c3 dot cn be the non-intersecting circles within let me write with centers at a1, a2, a3 dot up to an respectively, and radii so small that they lie within the closed curve, that is C. Okay, the larger curve C, right? Then if the function f of z is analytic in the multiply connected region, between capital C, the larger circle, the capital C, and those small circles, that region between the capital C and this C1, C2, C3. Okay, so this region, in these regions, okay, between C and C1, C2 dot Cn, right? Then by Cauchy's theorem, for multiple connected region, what we're gonna have, as I have already told you, the circle, the larger one, within which the small circles are enclosed, integration over that circle, the greater circle, f of z, integration f of z dz over c, that's going to be equal to integration of that function f of z over c1, similarly integration over c2 of the same function f of z dz, then dot cn. So integration cn f of z dz, that's what we're gonna have, right? So hope you have understood this. Now you see, let me go to the new slide. Let me copy this last step and let me go to a new slide. So here is the last step we have got. So this is the last step, right? So now you see, we know that. So what do you mean by residue? So note these things, that we know that what if z is equal to a is a pole of f of z. This is a function of complex number. Okay, so f of z complex variable, then function of complex variable f of z, this is a pole of that function, then what we can say that the residue at the pole is given by residue of the function f of z at a is given by 1 by 2 pi I integration over c, the closed curve f of z dz. That is what we got. So this implies integration over c f of z dz. C is the curve that surrounds the point A, right? That surrounds the pole A, right? So that's going to be equal to 2 pi I into residue of the function at A. We get this, right? So similarly, this must be equal to residue this must be equal to 2 pi I into residue of f of a1, because c1 enclose a1, right? Plus, so let me bring these things down. Okay, just wait. Okay, then similarly c2 enclose a2. If you see the diagram here, this is c2, right? It enclose a2, so that's why we can say that 2 pi I times residue of the function at a2 plus dot 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 residue 2 pi I times residue of the function at an, right? That's what we're gonna have. So let us take 2 pi I common, right? Then what we're gonna have, 2 pi I within bracket, we're gonna have residue of the function at a1 plus residue of the function at a2 plus dot 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 and so on, residue of the function at an, right? That's what we're gonna have. So what does it mean? This is sum of all the residues, okay, at the poles of the function. So this is what, this is equal to 2 pi I cross sum of, this is nothing but sum of all the residues at the poles within the curve C. Okay, so this is what residue theorem says. This is the residue theorem, hence proved. So hope you have understood this. Now let us solve two problems using this theorem. Okay, I have taken those problems from HK's book. Okay, so here is the first question. We are to evaluate this integral where C is the circle, this is the circle, given circle. So now let us draw the circle first. So this is the imaginary axis, suppose, and this is the real axis. Let us consider that way. And here is the circle, suppose. So here we have mod z only. That means this must be, the center must be at this origin. Okay. Okay, this is the real axis, and this is the imaginary axis. Okay. So, and 1.5, this mod of z 1.5 means radius is 1.5. So that's why this point must be 1.5. Okay, 1.5. So 1 must be lying within this circle somewhere at this point, and 2 must be outside the circle, right? So now first let us take the given function. So here is the given function. Let me copy the function. Let me copy the integral first. So this is the integral here, and the function f of z is here in this case. Let me write the function in. This is the function, this part here you see. So let me write this function here. So this is the function f of z. So first let me write the poles. Let me find the poles. How to find a pole? Just equate the denominator with 0. Okay, this is the denominator. So what is that? Z into z minus 1 into z minus 2, sorry, z minus 2, that's going to be equal to 0. Let me take that one as 0 in order to evaluate the poles. So if those are equal to 0, so we can, product of these three is equal to 0, then each of them must be 0 or any one of them must be 0. So let's take z is equal to 0, or z minus 1 is equal to 0, or we can say z minus 2 is equal to 0. So from here this z equal to 0 remains z is equal to 0. That's okay, fine. So z is equal to 1. From z is equal to z minus 1 is equal to 0, we're gonna have z is equal to 1, and from here we're gonna have z is equal to 2, right? Here we have got z is equal to 2. This is z is equal to 1. So here you can see z is equal to 0 and z is equal to 1. These two are within the circle, okay, and z is equal to 2, that's outside the circle, right? So what we're going to do here, so we can write that z is equal to 0 and these two are within the circle, which is mod of z is equal to 1.5, right? These two are within the circle, and z is equal to 2, which is outside the circle. Right, which is outside the circle. So these two are simple poles, as the degree is here, you know, as the order here 1, here you see power is on it is 1, so here also power 1. So they are simple poles, we can say. And if these are simple poles, then what will be the residue of the function at 0? So residue of this function, that's going to be equal to limit residue at simple pole of a function is given by limit z tends to the pole is 0 here, and z minus pole is 0 here, into f of z, the given function, right? So that's going to be limit z tends to 0, then z minus 0 is simply z, and the given function is this is the given function. Let me put the given function here. So f of z, this is the f of z. Here z cancels, so what we have, limit z tends to 0, 1 minus 2z divided by z minus 1 into z minus 2. If you evaluate the limit, then what you're going to have, 1 minus 2 into 1, 2, that's, and z minus 1, that's we have got 0, right? Z tends to 0 here, so this is going to be 1 minus 2 into 0, that's going to be 0, 1 minus 0, then 0 minus 1 into 0 minus 2, right? 0 minus 2. So here what we're going to have, so 1 by minus 1 into minus 2, that's going to give you 1 by 2, right? So this is the residue or residue of this function at the pole O. And what going to be the residue at f, residue of the function f at 1? That's going to be limit. Now the residue at 1, so z tends to 1, then z minus a, that is a is here 1, that means the pole is 1 here. Then f of z is again this. Let me write the function directly. So here you can see z minus 1 cancels. Let's evaluate the limit, and limit z tends to 1, z tends to 1 minus 2z divided by z into z minus 2, z into z minus 2. Let's put 1. So here it's gonna give you 1 by 2. Just wait. So that's gonna give you that. This is gonna give you 1 minus 2 into 1 divided by 1 into 1 minus 2, right? So this is going to be equal to, this is nothing but what, this is going to be equal to 1 minus 2 by minus 1, so minus 1 by 1, that's going to be equal to 1. So residue at f, residue of the function f of z at z is equal to 1, that is residue of f of 1, that is equal to 1. We have got, these are the residue. Okay, so now let me write these two residues. Let me take these two residues. Let me copy this one and let me go to new slide. So this is the residue, okay, and the other residue is this. So now you see, we are to evaluate this. Let me write this one, copy. Okay, so here is the integral that we are to evaluate. So according to residue theorem, so according to residue theorem, so therefore according to residue theorem, this must be equal to residue 2 pi into sum of all the residues at the poles within C. That means within the given circle. That's why we have ignored this z is equal to 2, which was outside the circle, right? So that's why we have ignored that. So we have taken only these two which are within the circle. So and 2 pi I, and what are the residues? Half and 1. So there's some that's going to be 3 by 2, right? And 2 pi I into 3 by 2, 2 gone, so we're going to get 3 pi I. So this is the answer. This is the value of this integral. So hope you have understood this. Now let's move on to next question. So here is the next question. We are to evaluate this integral, and the circle is given. Circle C is given this, mod of z minus I is equal to 2. Now you see, let me tell you something. So let me take this imaginary circle, imaginary axis, and this is real axis. So here this is the real axis and this is the imaginary axis, right? So when you see you have mod of z is equal to something, that is suppose r, then the center is at the origin, right? And the radius is r. Okay, now suppose if you have z minus a real number, any real number, suppose a, it may be 1, 2 or 3, is equal to suppose 3. Let me take it as 3, or let me take it as 1. Then here the center must be at plus a on the real axis. This is suppose 1, 2, and this is the point a. Suppose this is x is equal to a, so this is going to be the center. A is the center, and its radius is 1. Its radius is 1. Okay, and if you have plus a, then suppose this is minus a, and this must be the center with radius r. Sorry, here I have taken 1, so with radius 1. Okay, so now if you have imaginary number here, suppose z, you have minus 2i, mod is equal to suppose 1 or 2, maybe let me take 2. So then this is the imaginary axis, this is the real axis. So then this is I and this is minus I. So this is 2i, this is going to be minus 2i. Here minus 2i will be the center with radius 2. So this is going to be the circle. That's how we used to draw the circles, right? So now let me clean these things. So here, so this is the imaginary axis and here is the real axis. Okay, this is real and this is imaginary. So now here you see, here we have z minus i, so plus I gonna be the center. This is gonna be the center of the circle and radius must be equal to 2. So this is the circle, here is the center and radius is 2. That means this is 0 and this must be minus I, then this radius will be equal to 2. So hope you have understood this. And here you see, let me write the function first. Let me write the integral first. So this is the given integral and the circle C is z minus I is equal to 2. Now you see, let's find the poles. Before that, let me write the function f of z. This is the function of complex variable f of z, right? F of z. Okay, so let us equate the denominator with zeros. Z plus 1 whole square is equal to 0 and z minus 2 is equal to product of these two is equal to 0. That means z plus 1 is equal to z plus 1 whole square is equal to 0 and z minus 2 or z minus 2 is equal to 0, either both 0 or any one of them 0. Okay, so if this is the case, then we can say z plus 1 into z plus 1, that's going to be equal to 0 again. From here we're going to have minus 1, z is equal to minus 1 and minus 1, because we have z plus 1 whole square. That means z plus 1 into z plus 1. From that we're going to get two values of z and both are equal, those are minus 1. So there is a poles of order 2, right? And here from this part z is equal to plus 2. Okay, so z is equal to 2. That means here is suppose this is suppose 1 and this must be 2. As the radius is 2, here you see this radius is 2, so this 2 must be lying outside the circle, because if this center is here, then this length will be 2, but now here is the center and this is longer than this one, right? So if this is 2, then this side must be less than 2. Hope you have understood this. Okay, because if this is a right angle, this is if this is 2 unit, because the radius of this circle is 2 unit, this circle say is 2 units. So if this is 2 units, this must be less than 2, this side must be less than 2. That's why this 2 must be lying outside the circle. So this thing is clear to you, right? So now you see, this is outside C, right? So hope you have understood this. And this is within C, within the circle C. So now the pole of order 2. Now how to find the residue at the pole of order 2? So now let me go to the next slide. Let me copy this part. Okay, let me copy this part. Just wait. Let me copy these things and let me go to the new slide. Okay, so here is the new slide. Okay, so now this is pole of order 2, right? Now you see, let me tell you something. Know that if z is equal to a is pole of order n, then residue pole of order n of a function f of z, function of complex variable f of z, then residue of the function f at a is given by 1 by n minus 1 factorial. Okay, so let me write this here. Then n minus 1th order derivative, then here you see, let me write this one. Just wait. Okay, n minus 1th order derivative of z minus a into z minus a whole to the power z minus a whole to the power n into f of z at z is equal to a, right? So that's how we used to find the residue of a function at a point a, which is nth order pole, right? Nth order pole. So here the order is 2, pole of order 2, sorry, pole of order 2. So that's why, how to find that residue of the function at minus 1 is equal to 1 by, so as it is order 2, so it's going to be 2 minus 1 factorial, then n minus 1th order means here 2 minus 1th order, that is first order derivative of z minus a is minus 1 here, z minus a is minus 1 here, so it's going to be plus a plus 1, right? Plus 1 whole to the power n means n is z, n is 2 here, then f of z. That's how we're going to find the residue. Okay, so just wait, let me adjust these things and just wait. Okay. Here you see, just pause the video and note these things. Okay, so here you see, now what we're going to do here, this is going to be factorial 1, right? Factorial 1 is 1 simply, so then dz z plus 1 whole square, and what is f of z? This is f of z. Here you can see this is the f of z, z minus 1 into z plus 1 whole square into z minus 2. Now let us cancel these two, so just wait. So here we are to find the residue at z is equal to minus 1, right? At z is equal to minus 1. Okay, so what we're going to have, derivative of z minus 1 by z minus 2, and here we have to find the residue at z is equal to minus 1, right? So now here you see, if you differentiate it using this rule, u by v, its derivative is given by v derivative of u minus u derivative of v divided by v square. If you apply that, z minus 2 denominator, then derivative of the numerator z minus 1, right, minus numerator, that is z minus 1, derivative of the denominator z minus 2 divided by denominator square, that is z minus 2 whole square, right? So where we are going to find a residue at z is equal to minus 1, right? So if you differentiate it, then what you can have, z minus 2, if you differentiate z minus 1 with respect to z, that's going to be 1, and then we have z minus 1 here, and if you differentiate z minus 2 with respect to z, then this is going to be also again 1. And now you see, if you remove this bracket from here, z minus 1, as there is minus, it's going to be z plus. If you remove the bracket, then as there is minus, so it's going to be positive z plus 1, right? So it's going to be z plus 1, then divided by z minus 2 whole square, and at we are calculating the residue at z is equal to minus 1. So here minus z plus z gone, then here let me do it here, residue at here you see residue at the point z is equal to minus 1 of the function f is equal to, so here we have minus 2 plus 1, so that's going to be minus 1 divided by z minus 2 whole square, right? So at z is equal to minus 1, and if you put here minus 1, that's going to be minus 3, on squaring it, it's going to be 9, right? So we have got residue minus 1 by 9. We have got minus 1 by 9. So this is that is the residue, right? So now let me go to the next slide. So here you see, so let me go to the previous slide first. So here you see, this is the function. Let me copy the function, just do it. This is the function, and let me copy both function and integral. Okay, so here you see, this is the integral that we need to evaluate, and this is the function, and its residue, what we have got, residue of this function f of z at z is equal to minus 1, we have got minus 1 by 9, right? This is we have got. Just pause the video and note all these things, okay? And according to the residue theorem, therefore by residue theorem, you know that integration over c of the function f of z, here the function f of z is z minus 1 by z plus 1 whole square, 2 minus z minus 2, that is dz, that is equal to 2 pi I into sum of all the residues at the poles within C. But in this case we have got here you see, let me go to the previous slide. So here minus 1 is within this circle, minus 1 is within this circle, okay, and 2 is outside the circle, and residue at minus 1 is this minus 1 by 9, okay, minus 1 by 9. Then so as we have got only one residue, so that is minus 1 by 9, so let's put here minus 1 by 9 pi I into, here we're going to have minus 1 by 9, so that's why it's going to be equal to minus 2 pi I by 9. So that is our, so hope you have understood how to find how to use the residue theorem to evaluate definite integrals. Okay, so that is application of residue theorem, and we have discussed how to prove residue theorem and how to apply residue theorem here. And hope you like this video, and if you like my videos, then hit the thumbs up button. Also, if you're new to my channel, please subscribe the channel and don't forget to hit the bell icons. Okay, stay connected. Thank you for watching.